Very good afternoon. My name is Deivid Preciado Lopera. Today I am going to talk about the drude model. For this, will have this presentation that will have the following slides and at the end, example exercise and the use of a simple code in Python for this exercise. Uh, it should be noted that the slides only have a little of the information that we will talk about today, and that is was collected during this time at the end, and also talk a little about what books and internet links I use to talk about this topic. Finally, and before starting, it's worth clarify that on my one initiative and to challenge myself, I will make this video all in English and also to add something that it's being lately very showed today. Presentation was created by an artificial intelligence to which I feed which all the information I collected from my study. Its name is Tone and AI and is specifically created to make bases or presentations of any topic or information you insert. At the end, I will leave a link where you can try this AI. All this said, let's begin. The drude model, also to know as the drude theory, has provided by the German physicist Paul Drude in 1900. The Drude developed this model to explain the electrical and thermal properties of metal bases and a classical description of electrons in a metal. At a time, electrons were not yet fully understood and quantum theory had not been developed. Drude drew inspiration from the kinetic theory of gases and proposed that electrons in a metal behaved similarly to a gas of charges particulate in a sea of positive ions. This classic approach allowed Drude to provide a reasonable explanation for some of the observers' properties in metals. The Drude model assumes that electrons in a metal can be considered as negative charge particles moving freely. These free electrons interact with each other and with the metallic ions present in the materials. Collision between the electrons and the ions can cause changes in the electron's direction and velocity. Drude introduced the concept of reaction time or average collision time T, which representation the characteristic time between two successive collisions of an electron with the metallic ions. These average collision times plays an important role in describing the average velocity of the electrons and therefore the electrical conductivity of the materials. Despite its limitation, the Drude models was an important contributions to understanding the macroscopic behaviors on conductive metals of the time. It laid the foundation for the subsequent development of quantum theory, which provided a more accurately and detailed description of electrons in metal on the microscopic levels. It is important to note that the Drude model is a classical approximation and does not take into account quantum effects, such as the wave nature of electrons and the energy band structure in metals, wherever it is stays uses and pedagogical tool to introduce basic concepts of electrical conductivity and transport phenomena in metals. And now we talk about the more things about the Drude model. specific, the topics we'll talk about today is introduction and now assumptions of the drude model, electrical conductivity in the drude model, thermal conductivity in the drude model, limitations of the drude model, and modern applications of the drude model. So now, the drude model is based on a set of simplified assumptions that must be safety for its application. These assumptions are follows. Free electrons. The drude model assumes that electrons in a metal behave as a free particle that move unrestrictedly within the materials. This implies that the electrons are not thin-like bound the atoms and can move freely in the metal. Elastic collisions. The drude metal considers that collisions between electrons and metallic ions are elastic, meaning that there is no loss of kinetic energy during the collisions. In reality, collisions can be both elastic and inelastic, involving energy transfer between electrons and ions. Average collision time. The drude model introduced the concept of average collision time T, which represents the characteristic time between two successive collisions of an electron with the metallic ions. This average collision time is an approximation to describe the interaction of electrons and metal, but in reality, collisions can account with varying collision times. Constant electric field. The drude model assumes that the applied electric field is the metal is constant throughout the metal. This implies that there are not significant variations in the electric field along the metal, and the effects of each or imperfections are ignored. The thermal equilibrium. The drude model assumes that electrons are in thermal equilibrium with their surrounding. This means that velocity distribution of the electrons follows the Maxwell-Boltzmann distribution corresponding to the temperature of the material. It's important to note that these simplified assumptions of the drude model are approximations and simplifications that allow for an initial description of electrons' behaviors in metal. Whatever in more complex situations or at smaller scales, more advanced models such as the quantum theory of electrons in solids are necessary to obtain a more accurate and comprehensible description of electron behaviors. And now I'm going to be talk about the conductivity in the drude model. The drude model, the electrical conductivity of a metal can be understood as the measure of how easily electrons can move through the material in response to an applied electric field. The drude model provides a basic description of electrical conductivity in terms of electron density, average electron velocity, and average collision time. The electrical conductivity is related to these parameters by the following formula in the drude model. This formula, where N is the electron density in the material, number of electrons per unit volume, A is the charge of the electron, T is the average collision time, which represents the characteristic time between two successive collisions of an electron with the metallic ions. M is the effect mass of the electron in the material. According to the formula, electrical conductivity is directly proportional to the electron density and the square of the electron charge. It is also inversely proportional to the product of the average collision times and the effect mass of the electron. A high volume of conductivity indicates that electron can move easily through the metal, implying good electrical conduction capacity. On the other hand, low conductivity indicates greater difficulty in electron movement and lower electrical conduction capacity. The drude model allows for analysis of how different facts affects electrical conductivity. For example, an increase in electron density, a decrease in the average collision time, or a smaller effective mass lead to an increase in electrical conductivity. Whatever. It's important to the drude model is a classical approximation and account for effects. And now we'll talk to the thermal conductivity in the drude model. In the drude model, the thermal conductivity of a material can be understood as the measure of how easily electrons can transfer thermal energy through the material. In the drude model, thermal conductivity is related to the velocity of electrons and their average relation time. The thermal conductivity K can be calculated using the following formula in the drude model. We talk about this formula, where Cv is the molar heat capacity and constant volume of the material. B is the average velocity of electrons. E is the mean free path of electron, which represents the average distance and electron travel before colliding with other electrons or impurities in the material. According to the formula, the thermal conductivity is directly proportional to the molar heat capacity, the average velocity of electrons, and the mean free path of electrons. In the drude model, thermal conductivity is explained by the facts that electrons can transfer thermal energy through elastic collision with other electrons or impurities in the material. The average velocity of electrons and the main free path influence the amount of terminal energy that electrons can transport. It is important to note that the drude model is a simplified appropriation and does not account more complex. In summary, the drude model provides basic description of the thermal conductivity in terms of the average velocity of electrons and the mean free path. Whatever, for a more account of composition description of thermal conductivity in material, more advanced models that consider it in the other mechanisms, such as photons, are required. And now we talk about the limitation of the drude model. The drude model, despite being useful and providing a basic description of the phenomena in metals, also has several limitations and simplifications that need to be taken into account. Some of the limitations of the drude model are as follows. The first, does not consider electronic band structure. The drude model assumes that electronic behavior has free particles and does not take into account the electronic band structure in metals. The simplification does not allow for the description of a quantum phenomena such as band formation and electron dispersion in the material. Ignore electron-electron interaction. The drude model does not consider interaction between electrons in the metal. Ignore quantum effects. The drude model is a classical approximation and does not account for the quantum effects in the behavior of electrons in metals. does not consider electron scattering. The drude model assumes that collisions between electrons and metal ions are elastic and that there is not loss of kinetic energy. Whatever is really collision can be both elastic and inelastic, involving energy that transfer and electron scattering in the materials. 5. Does not consider the temperature effects. The drude model assumes that electrons are in internal equilibrium with the environment and follow as a Maxwell-Boltzmann's velocity distribution. Whatever at low temperatures, quantum effects such as electric collision and copper pair formation in superconductors needs to take into account. These limitations on the drude model make it a simplified description and not too suitable for all cases. In more complex situations or specific materials, more advanced approaches such as electric band theory and quantum theory. Electrons in solids are required to obtain a more accurate descriptions electrons' behavior in metals. And now we talk about the more application of the drude model. Despite its limitation, the drude model is still used in various modern applications in materials physics and electronic engineering. Some of the notable applications of the drude model includes electronics and semiconductors devices. The drude model is used in the design and characterization of electronic devices such as transistor, diodes, and integrated circuits. It helps understand electrical conductivity in semiconductors and materials and optimize device performance. Plasmonics and nanophotonics. The drude model is applied in the description of plasmons, which are collective oscillations of electrons at the surface of metals. These electronics excitations are used in nanophotonics applications such as enhancing sensibility in optical sensors, manipulation light, and that nanoscale and created nanoscale wave guides and antennas. Metal optics. The drude model is employed to describe the optical response of metal, includes reflection, absorption, and transmission of light. In these metallic fields, it's helped understand electron behavior and in the interaction with light and is used in the design of optical devices such as a mirror, filters, and surface plasmon components. Material characterization. The drude model is used as a characterization tool in material research. It allows for estimating important parameters such as electron density, electronic mobility, and electronic lifetime from experimental measures of electrical and thermal conductivity. Computation simulations. The drude model incorporated into computational simulations such as molecular dynamics methods and into calculation to describe electrons' behaviors in materials. This simulation enabled to study of electrons' thermal and optical properties of materials at different scales and conditions. And now we try to explain a little exercise. Suppose we have a metal which an electron density of this number and an electron mobility of 0.2. We want to calculate the electrical conductivity of the metal using the drude model. And solution, the equation conductivity can be calculated using the formula the drude model. And now this formula, this is the exercise, and where M is the electron density, E is the charge of electron, E and U is the electron mobility. uh, the electron mobility. So subtending the Gibbs values, we have this formula, and calculating the product. This is the result. And now we can plot this electric conductivity using a graph. On the x-axis we represent the electron density n on a logarithmic scale, and the y-axis we will represent the electrical conductivity on a line scale. So now let's go to view the code. The code is this. Electron density n of logarithmic scale base ds 10, and electrical conductivity calculated using the drude model and graph using this. This code is so simple because I use NumPy. It's a very good library and matplotlib to generate this graph, and we now to see this graph in the logarithmic base 10. And the result graph will show with the electrical conductivity increases with electron density following the linear relationship predicted by the drude model. The logarithmic scale on the x-axis allows for better visualization of the wide range of electron density. I hope this exercise and this graph help so better understand the application of the drude model in determining electrical conductivity in materials. And now we finish. I used 5 or 6 books, and this is more links to be used and different PDFs, and this is the link to use this app, this AI, to generate this presentation. Thank you very much, and see you later.